Oh, sorry, guys. I hope this isn't being recorded. It is.
I've only just turned it on, Adele.
It doesn't matter. Okay, so like from everything I've ever ID'd, and I do keep records, they were always stronger under long wave and invariably inert under short.
Yeah.
And so
I've got to check my scapulites at home because I think my scapulites at home are doing the opposite.
Well, look, hey, we know in nature there are anomalies. So
yeah,
look, don't worry so much about it tonight.
And the funny thing about ours is we supplied it. We thought it was citrine. We were told it was citrine.
What?
I just wait. Have you still?
Hey, scapulites uni actually negative. Citrine's U positive.
Yeah, but these are people who just look at everything and say, "Oh, that's CZ." When you go in and find out, it's definitely not. I'm surprised they haven't chucked it all in one jar.
Louise,
yeah,
bring him in.
Did you just say that you've got scapulite that you've got for sale that you were selling as citrine?
We had someone bought it for the ring. We were told it was citrine. Yeah.
Okay, because I'm trying to source some more scapulite for the collection here.
Yeah, I would have bought it off them if, yeah.
And it's proving a little bit difficult to track down. We need a couple more for the collection.
Go in and ask for all the shops to see their citrine. Go in with blacklight.
Okay, so keep this in mind. I know it's being recorded and I'll probably be sacked for saying this, but citrine versus scapulite, number one, Gem 2 question. Keep it in mind. Scapulite will give the UV, citrine no way, because Laura will do quartz to the death. And I'm opting out, darling. It's all yours, okay? Okay, Papa, bye.
So, a little bit of conversation there. What we're going to be doing tonight is fluorescence, and Adele just mentioned citrine, no fluorescence, scapulite will fluoresce. And the reason for that is that citrine is coloured by iron, and iron is a quencher, and we're going to be talking about that later tonight. I'm just going to close that door because I'm cold. There's a cold breeze in here. There was something else that I was going to pick up. So, chuck it on the polariscope.
Yes.
Both citrine and scapulite are uniaxial stones.
But they don't show the bullseye with the conoscope.
Very good. Yes. So polariscope with conoscope. Yes. Depends on whether you've got a stone in a ring and whether you've got access to orientator. But yes, absolutely. Very, very good. I wish some of my Gem 2s last year had have remembered that because they got all tied up in knots in mid-year Gem 2, misidentifying the scapulite.
So obviously, that is why they called it by the other moniker.
They called it crapulite. They hated it with a passion.
Tim told me he loved it.
Yeah.
He was the one who named it crapulite. Okay, so we've got to do the Chelsea filter. Was the last thing that we have to do, isn't it?
That is correct.
Yes.
Okay, so let's go slideshow from current slide, and I'm going to do this one sitting down again because I haven't stood up on my leg for that much time in like 4 weeks, and I'm a little bit nervous to stand up on my leg for another 2 hours. I'm just going to give it another couple of days because it still looks a little bit yucky. Anyway, doctor said don't panic. So Chelsea filter, finishing off from last week. Chelsea filter is a really, really simple little instrument. It's very simple to use. The observations that we make with it are also very, very simple and straightforward. So it shouldn't take that much time just to whiz through what the instrument is all about. Little bit of a preamble to start with. There is a reason why you guys do not have a Chelsea filter in your kits, and that's because at some point in the last decade, the way in which they manufacture the Chelsea filters has changed, and the new generation of Chelsea filters has the potential to give unexpected results, which are different to established observations that you can find in textbooks. So we don't provide you with the new Chelsea filters. The GAA over the past decade has done a lot of research. We've bought Chelsea filters from every manufacturer. We've bought ones that have different casings just in case they are different. We've taken them apart. We've tested them with UV vis to see which wavelengths are being transmitted. We've tried to talk to manufacturers to see if they can rectify the issues that we're having, and we haven't been able to get anywhere yet. So the lab has some of the older generation Chelsea filters for you guys to use during prac class. You can still buy Chelsea filters online, but those Chelsea filters may not give you the correct results with all stones. So just putting it out there as a word of warning. They're not that expensive to buy. It's just that the new ones aren't that great. So the Chelsea filter is a really simple little instrument. It's a screening tool that helps us to identify the colouring agent of gemstones in some circumstances. In particular, what we're wanting to screen for is the presence of chromium, particularly in a green coloured gemstone. And was that someone at home who wanted to ask a question?
Yeah, hi Laura. I can't see the slideshow.
Oh, that's not good. Thank you for letting me know because I had forgotten to share my screen.
Yes, so guys, if you've got messages, feel free to type them in. I'll check the chat, okay?
Okay, so we hadn't moved off from the first slide anyway, so we haven't missed that much of the slideshow. Okay, so the Chelsea filter is a really simple little instrument that is designed to absorb most of the visible spectrum, but allow the transmission of two very narrow ranges. One of those is in the red portion of the visible spectrum, and one is in the yellow-green portion of the visible spectrum. Was that another question at home?
Yeah, I asked Adele about this. I have an old Rayner refractometer that I refurbished and calibrated myself. It came with two filters. One was a yellow filter with a polarizing filter on it, which is obvious what that does. But the other one had a red and a slightly yellow-green filter in it. And I was asking what that was. Is there any reason why you would use a Chelsea filter on a refractometer?
No, not that I can think of.
Okay, because I'm still trying to figure out what it was for.
Yeah, look, because you said a red and a yellow, the red potentially so that you can measure the refractive index of the gemstone with the red, with the B Fraunhofer line. If you had the blue filter as well, then that could have been used for measuring dispersion. But other than dispersion calculations, I can't think of any reason why you would use a red filter on the refractometer.
Yeah, it's layered one over the other. So I was, if you can figure it out, I would be happy to know.
Okay.
When you have prac with David, bring it in because I think we'd all love to know what you've got.
I'm bringing the whole box in. There's a heap of stuff you guys are all going to want to see.
Okay, brilliant. Thank you.
So the red wavelength that the Chelsea filter allows through is approximately 690 nanometers, and the yellow-green wavelength that the Chelsea allows through is about 570 nanometers, so 570 and 690. And other than those two narrow regions, it's actually a fairly narrow band, not the actual specific wavelength. All the other wavelengths are absorbed by the filter. So what this means is that if the gemstone itself is transmitting one of those two wavelengths that are allowed through by the filter, then the gemstone will appear that color through the filter. And as we know from when we looked at the dichroscope and we looked at pleochroism in gemstones and the selective absorption of light, gemstones that are coloured absorb portions of the visible spectrum. So not all of the wavelengths are transmitted by coloured gemstones. And even if a gemstone is red, it so happens that it may not actually be transmitting the wavelength of 690 nanometers. And if a gemstone is green, then it may not actually be transmitting that particular color of the 570 nanometers in the yellow-green either. The Chelsea filter was developed in Great Britain by GEM-A, and it was developed primarily as a screening tool to help identify natural emeralds and separate natural emeralds from all other imitation green gemstones. At the time, back in the 1930s, when the emeralds that were available on the market were coloured by chromium, and the other known imitants and synthetic gemstones that were available were not coloured by chromium. So it was a very easy and quick test. The chromium in the emerald, even though emeralds appear green, the chromium actually has a transmission window in the red and passes through the red wavelengths of the 690 nanometers that the Chelsea filter is designed to show us. So you use a Chelsea filter over an emerald and it looks red. And this is because of the chromium. And if we have a look at the graph of transmission windows in emerald, then although emerald is green, the emerald is absorbing a band of wavelengths that straddles the yellow-green portion of the visible spectrum and the 570 nanometers. So emerald is absorbing the yellow-green and transmitting the red. But on the balance, our eyes still interpret the colour of emerald as being a green colour. Our eyes are blind to the red wavelengths that are being transmitted by the emerald. But the Chelsea filter helps us see those red colours. So the eye perceives colour because of the removal of particular wavelengths from the visible spectrum. And sometimes it's so finely balanced that we only need to remove one particular wavelength and our eye will see the complementary colour to the single wavelength that has been removed from the visible spectrum. So just because an item is green doesn't mean that it's only transmitting green light. There are other wavelengths that are being transmitted by that gemstone as well. So we have a spectral composition and a combination of wavelengths that are being transmitted by a gemstone. So when we're using the Chelsea filter, particularly on green gemstones, we just want to know, does the 690 nanometer wavelength that's associated with chromium, is that being transmitted by the gemstone? So if it appears red under the Chelsea filter, we can confirm that that stone has chromium in it. Now, the Chelsea filter since the 1930s has got a little bit more complicated because not all emeralds are coloured by chromium. Since the 1930s, new mines of emeralds have been discovered, and there are now emeralds on the market that are coloured entirely by vanadium rather than chromium. And the definition for an emerald has expanded from a beryl coloured by chromium to a beryl coloured by vanadium and or chromium and or vanadium. You can still get green beryls that are coloured entirely by iron, and they're a much weaker, paler, yellowish green colour. They're almost more the colour of a green quartz, or what's sometimes called on the market these days as green amethyst, which I hate that name, but a lot of people sell it as green amethyst. So that's the kind of colour that a green beryl will come in if it's coloured only by iron. But the vibrancy of the emerald can also be coloured by vanadium. If it's only got vanadium present, it won't show red under the Chelsea filter. Also, since the 1930s, there have been other gemstones that have been discovered that are also coloured by chromium. So we have Tsavorite garnet, which was not known in the 1930s. Tsavorite garnet is a grossular garnet that's coloured green by the presence of chromium. That will show a red response under the Chelsea filter. We've got chrome tourmaline, which was not known in the 1930s. And chrome tourmaline, being coloured by chrome, will also show a pink to red response under the Chelsea filter also. So the clue there is in the name with the chrome tourmaline, but there are a number of green coloured stones that will show a pink to red response under the Chelsea filter. So not all emeralds contain chromium, and some emeralds can also contain iron, which may dampen any response that we see from the Chelsea filter. And later on today, when we're talking about fluorescence, chromium is an element that is considered an activator, which means when chromium is present, the gemstone is likely to fluoresce. But if there's an amount of iron that is present, it'll also dampen down any fluorescent response that's associated with the chromium. In the 1960s, a true synthetic emerald made its way onto the market, and this also complicated things a little bit because synthetic materials, by definition, have the same chemical composition as the natural that they're imitating and the same structure. So they are a beryl, and because they're coloured by chromium, they are an emerald, and they're identical to the natural stone in every scientific sense of the word. But the synthetic material, they're usually optimizing the colour of the synthetics to imitate the best quality emeralds. So they want a really richly saturated emerald, and they get that by doping it with lots and lots and lots of chromium. So in the synthetic materials, we usually see a much stronger reaction because of the larger amount of chromium that is present. That doesn't mean necessarily that if you have a very high quality emerald, that a Chelsea filter will be able to distinguish the natural from the synthetic. There will always be a need to do additional tests on gemstones to verify the identity and how it was manufactured. So synthetic emeralds will also show red under the Chelsea filter, but usually a much, much stronger reaction to the natural gemstones. And then a lot of the green gemstones that we have on the market may also show a red reaction. So we've got the chrome tourmaline. Demantoid garnet is another garnet that can be coloured by chromium. We have Zavorite garnet and green zircon. Although green zircon is not coloured by chromium, the green zircon does transmit the red colour of 690 nanometers. So a lot of green zircons may show a pink to red colour under the Chelsea filter. So we have an instrument that in the 1930s was very, very successful. You could have a mixed parcel of green gemstones and you pass the filter over it, and any gemstones that appeared pink or red must be emerald, because there were no other possibilities. And now, 100 years later, or almost 100 years later, we have a situation where any number of other natural gemstones and potentially a few synthetics may also show a pink to red response under the Chelsea filter. In addition, the Chelsea filter was shown to be very effective at identifying or screening synthetic spinels. It was not designed to detect cobalt, but the synthetic cobalt blue spinel, which is the really richly saturated royal blue or cobalt blue colour synthetic spinel, also transmits 690 nanometers. So synthetic cobalt blue spinels are usually very bright red under the Chelsea filter, and most other blue stones will not show a red response under the Chelsea filter. And I do want to say most other blue stones, Sri Lankan blue sapphire can sometimes have a colour change effect where we can have a purple colour and a blue color, depending upon which lighting conditions you view it under. And sometimes they can have a subtle purple undertone to them under natural sunlight as well. The stones that have the purple color change because they have a small amount of chromium that is present in them. So chromium causes the red color of ruby, which is a red corundum. Blue sapphire is iron and titanium, coloring agents of blue sapphire. But if you get a blue sapphire with iron and titanium and you mix in a little bit of chromium, blue and red make purple. So purple sapphires are a combination of iron, titanium, and chromium. And because of the chromium, a blue sapphire may show a pink response under the Chelsea filter also, which is kind of just a little bit of fun. Because it's this little innocent little filter, but you can get a little bit of an insight into the chemistry of the gemstone. And you can get a couple of different blue sapphires that look similar in color, and you pass the filter over and you go, oh, actually that one's got a little bit of chromium. That might color change, and then you put it under your incandescent torch and see it go a purple color. So it's a little bit fun. So cobalt, I went off on a little bit of a tangent there. Synthetic cobalt spinel, bright red. If it's a blue stone and it's showing a really strong red response, it is going to be a synthetic cobalt spinel. There is a natural counterpart, a natural cobalt spinel, but they're really, 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 really super rare. There's a deposit in Tanzania. There's a deposit in Vietnam, and I don't think I've got that stone with me tonight. I had it here last week. In Luc Yen, up in the north of Vietnam, there's a spinel deposit with cobalt. They're very rare and they're very expensive, so it's unlikely that you will come across naturally occurring cobalt spinel. So if you've got a spinel and it's got a cobalt reaction, it's probably going to be synthetic. What else do I want to say? I've said about the colour change blue sapphires from Sri Lanka. They're lots of fun. And in summary, the Chelsea filter is used to indicate the presence of chromium and cobalt in various gemstones. Now, in terms of how we use the Chelsea filter, I haven't got this in my PowerPoint, but I should have it in my PowerPoint. If you would... Oh, that's okay. So if you had your Chelsea filter, has anyone got a Chelsea filter here instead of me trying to use a texter? Gem kit? Yay! Oh no! I've just said no one has Chelsea filters, and now I'm asking for the Chelsea filter.
It's a new one.
Hey! Okay.
But it's still, yeah, I haven't tested it.
Yeah.
It could be a good new one.
No, it's not a good new one. Okay, so for those at home, piece of white paper and Chelsea filter. What you're going to do is put your gemstone table down on a white piece of paper and bring that to a light source that is incandescent or yellow based. In your kit, you have a pen light that is an incandescent pen light, and you can use that to illuminate your stone. Otherwise, there is a lamp at the front teacher's desk, which is incandescent, and the tiny little gooseneck lamps at your desk that's attached to the desk, they're incandescent. They don't always work. So what you're going to do is put your gemstone table down on a white piece of paper, bring it underneath the incandescent light so that the yellow light is illuminating the paper and the gemstone. You're going to bring your Chelsea filter up to your eye as close as possible, and you're going to view your paper from maybe about 20 centimeters away. And you're going to look at the stone and see whether the stone is showing shades of pink or shades of green. Now, according to the strict theory, your stone will always only be shades of pink or shades of green. In reality, they can show like a black color, or they can be a flesh tone type color or a skin tone type color, which is still a shade of pink. But we're going to try to write down the color that we see. For weak colored stones, the reaction might be very weak and you might not know what colour you're seeing, or indeed if there is a change from what you're seeing. So a little trick is when you're looking at the stone, bring the Chelsea filter up and then back down and up and back down while looking at the stone, and just go a couple of times up and down, and that way it flicks between the colour, the actual colour of the stone, and the colour seen under the Chelsea filter, and will give you a little bit more of an idea. If it's screaming red at you, it's going to be a really obvious reaction. You're not going to need to do any like trickery with moving the filter around. But that's a little trick just to see pale coloured stones. Just flick the Chelsea filter up and down. Limitations of the filter: size, shape, and transparency of the stone will all influence the intensity of the result that you see. So even a cobalt blue synthetic spinel, if it's only 2 mil round, it's going to be a very pale body colour by comparison to a big 10 mil round stone, and it may not show the intensity of reaction. Same thing for an emerald. Small green emerald versus a big emerald. The larger stones are going to show a bigger reaction, and darker stones are going to show a more extreme reaction because there's going to be more colouring agent in there also. And yeah, that's just something else. So I've got a couple of tables here that explain different reactions that you may see. Alexandrite is a colour change variety of chrysoberyl. The colour change is caused by the presence of chromium, and where we have chromium, we should see a red reaction under the Chelsea filter. Some of these stones, aquamarine that says distinctly green, this is where these new Chelsea filters give erroneous results. One test that we have, and I kind of say test in inverted commas because it's not my go-to test, something like a blue topaz and an aquamarine of the same body tone. Your aquamarine should be distinctly green and your blue topaz should be a flesh-coloured pink. There are other tests to confirm whether it's aquamarine or topaz, but aquamarine and topaz, those subtle reactions are what this Chelsea filter doesn't do very well. So that's where the Chelsea filter, that's where we decided we didn't want to go with the new Chelsea filters. Tsavorite garnet's coloured by chromium. Chrome tourmaline is coloured by chromium, whereas a green sapphire is coloured by iron and will appear green. A peridot is coloured by iron and will be green. So you can go through the rest of the tables by yourself and try to learn those expected reactions with the Chelsea filter. But it will also help if you start to learn which of the transition elements cause the colour in which gemstones also, because that goes hand in hand with the reactions that you're going to see with the Chelsea filter. Any questions on the Chelsea filter?
Do we have to learn all these for the end of year exam? All the reactions we have to memorize?
Yeah.
Not for mid-year.
Not for mid-year, no. For the end of year and for the mid-year, what is examinable is strictly what is in the GAA notes. So when we say learn all the reactions, I would love you to learn all the reactions. That would be really, really good. But I've also spent a lot of time on my PowerPoints on trying to find information. If it's not in the GAA notes, I try to find it to put in the PowerPoints to make your life easier. And then I sometimes forget what I've put in the PowerPoints and what's not in the notes. So if this information is not in the notes, you won't be examined on it. But it's really good information to have, and it's still like a go-to reference for you.
Yeah.
So, yeah.
Okay. So we just find the thing.
So what's in the notes is examinable, but please don't disregard studying my PowerPoints. Okay, so I'm going to flip over now to the next PowerPoint. So we've got to cover specific gravity, fluorescence, and magnetism tonight. So I don't think we're going to get there, but we're going to give it a go. Specific gravity, we've got a weighing instrument next door that we need to teach everyone how to use that will determine the specific gravity of a gemstone, and alternative word that we use for specific gravity is sometimes density, but the more correct term is specific gravity. So we're going to go through tonight what specific gravity is, how we measure it, and we measure it using a method called hydrostatic weighing, which means that we weigh the gemstone when it's immersed in water. And we're going to show you how we do those calculations and how we get the figure for the specific gravity. And we're going to go through a procedure of how we use the balance and which gemstone materials are appropriate for use and which gemstone materials it's not advisable to do a specific gravity test on. For example, when a gemstone is in a piece of jewellery or a ring, measuring the specific gravity is not going to give you an answer of what the gemstone is. It's going to be a combination of the gemstone and the metal, and that information is not going to be of any diagnostic importance of being able to identify the gemstone in the ring. So we can only do a specific gravity measurement on gemstones that are loose. After specific gravity, we're going to go on to fluorescence and using ultraviolet light. We've got two different types of ultraviolet light that we use in gemology. We call one short wave and we call the other long wave. We need to know what the wavelengths of those ultraviolet light sources are, and it'll become apparent why we call one short wave and why we call one long wave, because one has a shorter wavelength than the other. We'll explain what causes fluorescence or luminescence. We'll go over some of the typical fluorescent responses from some of the gemstones that we're going to be testing in the lab. And then, because this year's the first year that we've added magnetism into the syllabus, I've added it into the PowerPoint, but I forgot to add it on the summary sheet. So the other instrument that we're doing tonight is how to use a rare earth neodymium magnet, and the procedure for testing stones with the magnet and what types of gemstones are going to show a weak magnetic response to a magnet. The neodymium magnet's a really, really strong super magnet, and even with that really strong super magnet, most gemstones will not show a significant response. We need to use a really strong magnet to get any kind of magnetic response from gemstones. Spoiler alert, iron is very, very magnetic. So gemstones that contain a large amount of iron are magnetic or show a magnetic response when they come close to the rare earth magnet. So garnets are really, really good for playing with magnets.
Is there a specific measure to say how magnetic the rare earth magnets we use in gemology are? Because we need to put it that's like strong, how strong the bond is, like
yes.
Weak.
Yes, yes, magnets do have a measurement on their strength.
Yeah.
I don't off the top of my head know exactly what those definitions are, but I know that we use I think it's an N52 neodymium magnet.
And there's like the standard for gemologists.
That's the standard for gemologists, yes. If you go to some place, if you haven't already got one from Sally, if you go to some place like JCAR, you can buy neodymium magnets. But they don't always sell the N52 that we want.
Yeah.
And they sell a range of different types of neodymium magnets at different price points and different strengths. So we want the N52.
Yeah.
Okay, so jumping into specific gravity. Specific gravity is defined as the ratio of the weight of a specific material, so the weight of our gemstone compared to the weight of the same volume of pure water when measured at standard atmospheric pressure and at 4 degrees Celsius. That's the extended theoretical definition. When we come to measuring specific gravity in the lab. Standard atmospheric pressure just means, in standard, atmospheric pressure in the room. We're not going to have to make any special allowances because we're taking measurements that are outside standard atmospheric pressure. So it just means room atmosphere. And at 4 degrees Celsius, I'll talk a little bit about this in a couple of slides' time. But although the theoretical definition of specific gravity specifies 4 degrees Celsius, the word that I'm looking for, the sensitivity of our balances and the accuracy of our work with gemstones means that we don't actually need to worry about taking measurements at 4 degrees Celsius. Standard room temperature provides the accuracy that we need for specific gravity calculations of gemstones. But it's the ratio of the weight of a specific material to the weight of the same volume of pure water. And we can also refer to it as density. Specific gravity is another one of those supporting tests, similar to what I was just saying about the Chelsea filter. Specific gravity by itself is never used to identify a gemstone, but when taken in combination with a number of other results, especially when some of the results from instruments that we use may overlap, specific gravity may help to separate some pairs of gemstones when we're getting to the pointy end of trying to decide what gemstone it is. So it's not a significant test that we do, but it still has some relevance and some importance, but we don't use this by itself to identify a gemstone. The most important test that a gemologist always has in their toolkit is first and foremost their eyes, visual observations of the stone, hand lens, the inclusions that we're seeing in the stone, and then optical measurements such as the refractive index of the gemstone is going to be much more important, but we always look at other results and other instruments as well. And we will frequently do a specific gravity test on an unset gemstone. If you go further in with jewellery, if you go on to become a jewellery valuer, because you cannot do a specific gravity test on a gemstone that is set, most gemologists dealing with stones that are set in jewellery won't use specific gravity as a routine test and don't rely on specific gravity. Also, at the moment, the instruments or the weighing instruments for specific gravity, if you go the high-end instruments like we have next door, they cost in the region of about $3,500 for the balance. So a lot of gemologists setting up a home lab at home, it's one of the last instruments that they get at home. You can get little conversion kits to turn a little diamond scale into a specific gravity instrument, but it's never got the accuracy of the more expensive balances that we have next door. We use water when we're doing our specific gravity test. Any liquid could be used to immerse a gemstone in to take our measurements, but we use water, and there's a couple of reasons why. One, it's non-lethal. It's free or cheap, and it's very readily available. There have been other liquids suggested for specific gravity testing, and a number of the other liquids that have been suggested come under what is called heavy liquids. We used to have heavy liquids or knowledge of heavy liquids in the syllabus, but they're not in the syllabus anymore. But a number of the heavy liquids that we used are carcinogenic, are very dangerous liquids and require a lot of care in how we use them. By definition, the specific gravity of water is 1, and that's another reason why water is really useful for performing specific gravity tests. if we were to use a liquid of another density, so a heavy liquid, then the calculations become a little bit more complicated, because by definition, specific gravity is the ratio of the weight of the gemstone compared to the weight of an equal volume of water. So if we're using something other than water, then we need to do a conversion calculation to bring it back to the density of water. But what do we mean by specific gravity of water is 1? That basically means that 1 litre of water weighs 1 kilogram. So it's very easy if we have a container, if we can measure the amount of water in the container, then we can very quickly also identify how much that container is going to weigh. When we're talking about specific gravity of gemstones, because it is a ratio compared to an equal weight of water, then what that means is that it's heavier than water by a certain amount. So for example, corundum has a specific gravity of 4.0 is the common number quoted. In reality, it ranges from about 3.95 to 4.03 depending on the stone, but with an average of about 4. So that means that a corundum or a sapphire gemstone is 4 times as heavy as water for the same volume. So instead of having a 1 litre container filled with water that weighs 1 kilo, if that same container was instead filled with 1 solid corundum crystal, it would weigh 4 kilos rather than 1 kilo. So that's what we mean by specific gravity. We are measuring that density of the gemstone and how dense it is compared to water. Specific gravity is also a ratio, and because it is a ratio, it means that it has no units of measurement. So we drop all of the units of measurement and we just quote it as a number. And for our specific gravity measurements for gemology, we quote specific gravity to 2 decimal places. So corundum doesn't have a specific gravity of 4, it has a specific gravity of 4.00. The decimal places can become important depending on which gemstone that we're looking at. So let's have a look at why we said at 4 degrees Celsius. At 4 degrees Celsius, water is its most dense. So though we say by definition water has a specific gravity of 1, at 4 degrees Celsius, if we round it up, it has a specific gravity of 1, but it's just very, very slightly different. But as we increase the temperature of the water, we increase the kinetic energy in the water. And the kinetic energy is how the atoms are moving around and vibrating. And the more they move around and vibrate, the further apart they get from each other, so the less densely packed the atoms are, which means for the same volume of water, it will weigh less. And as you can see, as we increase the temperature and as we decrease the temperature from 4 degrees, the density of the liquid reacts or changes according to the temperature and the amount of kinetic energy that's present. So the definition says we want to use water at 4 degrees Celsius because that is its most dense. In reality, these figures are actually measured in grams per meters cubed, but these figures quoted to 4 decimal places. We're going to be quoting our figures to 2 decimal places, and even at room temperature, we're still going to get within an error margin that's acceptable for gemology, and we're not going to worry about what temperature the water is. A little bit of a introduction into mass versus weight. This can get a little bit confusing if you're trying to do some reading outside of the GAA notes and you start picking up physics textbooks or some of the old mineralogy textbooks. They'll use differing terminology. And over time, the terminology that we have come to use every day is oversimplified, and scientists use slightly different words with slightly different definitions. So when we talk about our weight, when we weigh ourselves on scales and we get a measurement in kilograms, what we're actually measuring is our mass in a scientific sense, not our weight. Weight is mass of an object that's being acted on by gravity with that extra gravitational force, and it's measured in newtons. Little bit of semantics, but I just want to throw it in here. The mass of an item refers to how heavy that item is, and the heaviness of the item is directly related to what types of atoms that item is made up of, and how tightly packed those atoms are within that structure. And particularly with gemstones, how tightly packed that structure is can have a big difference on the density of the gemstone that we're measuring. So weight's dependent upon the gravitational force acting on a body, but because we never leave planet Earth, or because very few of us get the opportunity to leave planet Earth, we don't really notice the difference between the effects of mass and the effects of weight. If you climb up Mount Everest, then there might be very, very slight differences in scientific measurements that are taken. But those terms we now use as interchangeable. So unit of measurement for mass is the kilogram, while the unit of measurement for weight is the newton. But we tend to use kilograms to denote weight. Was that a question at home? No?
Yes, it is. Yes.
Hello.
Kavita, you raised your hand. Do you have a question? I don't have a text and I don't have a question here, but...
Hello, can you hear me? Can you hear me, Laura? Laura, can you hear me?
Yes?
Yes, I have a question. Does atmospheric pressure have any effect on the nature or structure or whatever on the gemstone?
No.
Wonderful.
It doesn't have any effect.
Thank you. Thank you.
Okay. I'm used to having the speakers behind me, and now I'm like, that's a little bit, confusing that they're in the roof at the back of the room. Anyway, so density of an object is a property which is independent of location and size. It's defined as weight per volume and can be represented by grams per cubic centimetre cube. On the next slide, however, I've got it as kilograms per metre cube. And to convert between the two units is not that difficult. It just depends on what you're measuring in and how you quote it. So one of the measurements for density, it can be quoted as density. Here I've got it as kilogram per metre cubed equals mass divided by volume. And that's a very quick way of getting the density. And what this tells us is how heavy an item is for its size. So this tells us the difference between a piece of lead and a piece of marshmallow. If they're both the same size, if we've got a standard size marshmallow and a piece of lead the same size as the marshmallow, the lead has a much higher density. So it's made up of different atoms that are a lot heavier and a lot denser packed than the marshmallow is. So it has a much higher heft also. When we place it in our hand, it feels heavier. Looking at some examples of gemstones, diamond has a specific gravity of 3.53, which means that it's 3.53 times as heavy as water. quartz has a specific gravity of 2.65, meaning it's 2.65 times as heavy as water. And by comparison, graphite is just 2.23. And I've chosen these gemstones to illustrate the differences both of chemical composition and also of the structure of the gemstone material as well. So the silicon and the oxygen that comprise quartz, silicon and oxygen are heavier atoms than carbon is. But quartz is not denser than diamond. And that tells us that the structure of the diamond is a lot more compact than quartz. So we shove in a lot more carbon atoms into the same space as what we do the silicon and the oxygen atoms in the quartz. So the diamond is heavier. But then have a look at graphite. Graphite is also made up of carbon. It's a polymorph of diamond. It crystallizes in a different crystal system, but by comparison, its specific gravity is considerably less than diamond. So it's made up of the same elements, but therefore the structure must be contributing to the difference in the specific gravity. So in graphite, the carbon atoms are a lot more spaced out. They're not as densely packed as they are in diamond. So we've got two different contributing factors. We have the chemistry of the stone, which elements make up that particular gemstone, and also how tightly packed those elements are. And they're going to combine together to give us the specific gravity of the gemstone. And to a certain extent, each species of gemstones has a unique specific gravity. Some gemstone species will overlap, and as we'll discover a little bit later, some gemstone species actually have a range of specific gravity results that we can get between upper and lower limits. So we have a narrowly defined range of values that can define a family of gemstones. Heft, damn it, that's what I needed to get. Do you want to just give me 2 seconds? I'm just going to run into the lab because I forgot to get schizophrenia. Okay. These are just out of the display cabinet that's next door, and they are different shapes and they are different, slightly different sizes. So this is a little bit ish, but I've got 3 different gemstones. So as you pass them around, what I want you to do is put one in your hand at a time and just kind of lightly bounce them in your hand, and then compare them to the other stone and bounce it lightly in your hand and see which one is the heavier stone, or which stone you expect to have the higher specific gravity. So heft gives us an idea of how heavy an object is, and sometimes we form an idea in our brain of how heavy we expect an object to feel, and then when we pick it up, we go, oh, gee, that was heavier than what I expected. Over time and with experience, it may sound a little bit crazy, but we get to know how heavy a gemstone expects to feel in our hand. So you pick up like a 6.5 mil round diamond, and you feel the 6.5 mil round diamond in your hand, and if you're used to handling loose stones, you get to feel, or you get to used to how a 6.5 mil round diamond feels in your hand. And then you come along with a cubic zirconia, and the cubic zirconia is almost twice the specific gravity of the diamond. And for a 6.5 mil round cubic zirconia, you pick it up and you go, ooh, that was heavier than what I was expecting. So that's heft. And I encourage everyone in prac class just to pick up a loose stone. Each time you're looking at a loose stone, pick up the loose stone with your hand and just get a feel for how heavy it feels. Because some gemstones will feel lighter than you expect, and some gemstones will feel heavier than what you expect. So heft can be a useful kind of tool. A zircon is about twice as heavy as an opal for the same size. That kind of sounds a little bit crazy from the perspective of a zircon is transparent and faceted, and an opal is usually cut as a cabochon and shows a play of colour, and you never see a play of colour in a zircon. But the heft of how different they feel, one is a lot lighter, the other is a lot heavier. Cubic zirconia is twice as heavy or more than quartz of the same size. And it's almost twice as heavy as the diamond of the same size. So that's just a little bit fun. As those stones go around, one is a cubic zirconia, one is a moissanite, and one is a quartz. The moissanite's got a specific gravity of 2.25 from memory. Quartz was 2.65, and the cubic zirconia is going to be about 5.5, could be as much as 6, depending upon what type of cubic zirconia it is, what the stabilizing agent is. And I haven't tested it to know which one. So it'll be interesting to see which one you thought was the heaviest as it makes its way around the room. Okay, so determine the specific gravity. There are two main methods that we have to determine the specific gravity of a gemstone. One's known as the buoyancy method, which is by a suspension in a liquid, or the hydrostatic method of measuring specific gravity. And the other one is by using heavy liquids. Now you guys are fortunate because we don't examine heavy liquids anymore. When I went through and did gemology, we had to know all the different types of heavy liquids, what the specific gravity of the heavy liquids were, how they could be diluted to achieve specific gravities of a certain amount. And we never got to play with them in the lab because the chemicals were too dangerous, that it was all theoretical.
Hey, I brought toluene in for David. I put it in the cupboard. I don't know.
Yeah. Anyway, I'm not aware of many gemologists or labs in Australia that are still using the heavy liquids. So we're glad we've taken them out of the syllabus. Okay, so hydrostatic balance. This is an image of a standard hydrostatic balance for determining specific gravity. It's an digital analytical scale, and it's got the ability to weigh the gemstone out of water, which we refer to as in air, and we weigh the gemstone while suspended in water. So at the base of this instrument, we've got a little round weighing platform, which in this photo looks to be a little bit kind of grey or black colour. And that's where we'll place our gemstone to weigh it in air. And then when we want to weigh it in water, we need to place the gemstone inside the basket that is suspended in the beaker. You'll also notice that this particular instrument is encased in glass, and it's got a couple of doors on either side of the instrument and a door at the top of the instrument that can be opened and closed. These instruments are very, very sensitive. They're sensitive to airflow, they're sensitive to temperature, they're sensitive to vibrations and movement, which is why we need to be really, really careful when we're using the instrument so that we get a really accurate measurement. But the doors are here to close the doors so that the airflow in the room doesn't affect the specific gravity measurements that we're getting. Okay, straw poll in the room. Who thought that the black stone was the heaviest stone? Who thought that the yellow stone was the heaviest stone? Who thought that the pink stone was the heaviest stone? Yay! You all passed the heft test. The pink was the cubic zirconia, the black was the moissanite, and the yellow is the quartz. And all three of those gemstones are also synthetically produced.
So the quartz is the lightest one, yes?
The quartz is not the lightest one. No, the quartz is the lightest one, yes. Sorry, 2.65 for quartz, 3.25 for the moissanite. I was initially going 2.25 and then I went, no, that's wrong. Yeah, so 3.25, 2.65 and about 6. Yeah. Okay, so it's very sensitive. This instrument is very, very sensitive to air movement, which is why when we're weighing stones on the instrument, we have to have the doors closed while the instrument is calculating the weight of the gemstone. The hydrostatic balance works on the principle of Archimedes' principle, and it's a way of determining the volume of an item and therefore the weight of the volume of that item by immersing that item or submerging that item in water and measuring the loss of the weight of that item when it is submerged in water. So we can work out the volume of the item that we are trying to measure, which can be very, very tricky to try to work out the volume of an irregular shaped object. If we're just dealing with a box and we've got length, width and depth, a volume measurement is really, really easy to do. But for something like a gemstone that's got 50 or more little facets on it, all different angles, the pavilion of the gemstone is shaped a little bit like a cone, and we have got formulas for working out volumes of cones, but then the crown is shaped differently. So it's a very irregular object and would be virtually impossible for us to try to calculate out the volume of that gemstone if we had to do it mathematically and manually. It's an impossible job. But Archimedes worked out many moons ago that it's possible to calculate the volume of an item by immersing it in water. So when a body is immersed in water, there's an apparent loss of weight. And we all know that from getting into a bathtub or going down to the pool, that when we are in water, we feel lighter. And that's because when our body is in the water, it displaces some of the water. So when we get into the water, the level of the water rises. The level of the water rises by the same volume as what we are as our body. And the loss of weight that we feel when we're in water is also equal to the weight of the body of water that has been displaced when we jump into the pool or to the bathtub. So the loss of weight is equal to the weight of the displaced liquid. And this is how we're able to calculate the volume of our gemstone using the hydrostatic balance and immersing that gemstone in liquid. So Archimedes first developed this principle to try to test the purity of gold. So by knowing what the specific gravity of pure gold was, he was able to test various items that were not gold or were not pure gold and to work out what the purity was. So the loss of weight of the body while it's immersed in water is the same as the weight of the volume of the displaced water, which is equal to the volume of the body of the item that's being measured. This is what was known as the Eureka can, which was Archimedes' first setup. He obviously didn't have the digital weighing scales that we have these days, but what he had was a specially designed beaker that had a little spout that came out at the side, and underneath that spout he would put a measuring cylinder. He would fill the beaker up until the level of the water or the meniscus was just under the level of the spout. And then when he sunk an item into the beaker, the water level would rise because the item had been placed in the water. The water level would rise. It would rise by the same volume of the item that was being measured. And because the water level was just below the spout, when the water level rose, it spilled out of the spout and fell into the measuring cylinder. So therefore he was able to measure the volume of the water that was displaced, which was therefore the volume of the irregular shaped item that he was wanting to try to calculate. Was that a question at home?
No, just a comment. He actually realized this when he immersed himself in the bathtub. And when he did that, yes, and he ran out naked in the street screaming, "Eureka, Eureka!"
There was, just as a little segue, about a decade ago, there was a crime series from the US called Numbers, which had two brothers. One was a PhD mathematician and one was a FBI agent. And they were dealing with murder cases and things, and they teamed up together to solve these murders. And in the first season, they had a woman who was murdered in a bathtub, and then the body was removed from the bathtub and disappeared, and they were trying to identify the person who was murdered and find the body. And they identified the person using Archimedes' principle because of the water level that had been left behind on the bathtub, and they were able to work out therefore how tall she was and how much she would have weighed, supposedly. So
many variables to that.
Yeah.
So there were so many variables. So yeah, Eureka moment. Okay, so the density of the object is calculated by dividing the weight in air by the weight of the volume of the water displaced by the object. And the volume of the water displaced by the object is also equal to the loss of weight of the item while it's immersed in the water. So it's a very, very simple little calculation. We take two measurements on our scale. We have one measurement of the gemstone weighed in air, and then to calculate the loss of weight when the item's weighed in water, we weigh the item again when it's suspended in water, and the loss of weight when suspended in water is the weight in air minus the weight in the water. And that gives us our specific gravity. So it's a very, very kind of complex scientific principle. It was a leap of logic many, many moons ago, thousands of years ago. But now we've got this little digital measuring device, and with two simple calculations, we not only get the volume of our gemstone, but we're also able to calculate its specific gravity, which is very, very helpful to us. Was that another question?
Laura, you have a question, yes.
Yes, I do. Yes, I do have a question. Buoyancy does affect this equation.
Sorry?
Buoyancy,
Buoyancy affects this situation. What situation?
this equation, because when the buoyancy increases, then the loss of weight of the object increases.
if you add a drop of liquid detergent, like dishwashing liquid, it takes away the surface tension, and that should reduce buoyancy and air bubbles.
Yeah, that's in terms of gemstones. But basically, as a principle, because if you jump into a lake here, or if you jump into the Dead Sea, it does make a big difference
Yeah.
to your the weight, your weight.
It gets a lot more complicated. Yeah, but for the gemstones that we're testing,
It's clear water.
it's in clear water. The gemstones that we're testing are crystalline. They're very small, and the balances that we use are very, very accurate.
Yeah, thank you. Because this is my physics.
And if we use as was it Louise who said a little bit of detergent in the water reduces surface tension?
Yeah.
So we can make a few corrections for some of the issues that may present themselves.
Yeah, but the water has to be clear water. That's it.
Absolutely.
Next time you are swimming in the Red Sea, cover yourself in detergent. You might.
I might not even get wet. I might not even get wet.
No, but what you're saying is perfectly correct. It's on your little gemstones.
Yeah.
We use distilled water.
Ah, right. That's what we call clear water. That's what we call clear water, in physics,
Yes. So gemstone species will have a characteristic range of specific gravities, and even some varieties of some gemstones may have specific individual ranges of specific gravities. So individual varieties that are a different color, they're a different color because of the different trace elements and the different transition elements that give rise to those colors, and they may be different weights. So species of varieties of different colors may have subtle differences in specific gravities. Some gemstones, as we learned when we did chemistry, are part of solid solution series. And when we have solid solution, we can have individual places within the crystal lattice, which can be occupied by different types of elements. And depending upon whether you have the lighter element or the heavier element present is also going to affect the specific gravity of your gemstone that you're measuring. So for example, coming back to corundum, as I said earlier, corundum family has a range of specific gravities from about 3.95 to about 4.03. And there can be a range of factors that contribute to an individual stone testing towards the higher end of that narrow limit or the lower end. Chromium is heavier than the titanium. So rubies tend to have a higher specific gravity than a blue sapphire. But it can depend on how much transition elements is present, and it can also depend on other factors such as inclusions that are present within the stone as well. Stones that are heavily included, not a couple of tiny little crystals, not a few healed fractures, but stones that are very heavily included, the inclusions may affect the specific gravity of the stone that you're testing and cause it to be slightly higher or slightly lower than the range that you would expect for that particular gemstone. So we have solid solution, we have transition elements, and we have the presence of the inclusions. So I've mentioned the inclusions as well. So listing the specific gravity of some colorless gemstones, these are taken from our Blue Book of Constants. Quartz is quoted as 2.65. Quartz is not quoted with a range of specific gravities, and that's because the coloring agents for quartz are color centers and not large amounts of transition elements. So quartz tends to be fairly uniform in its specific gravity or in its density. Goshenite is the colorless variety of beryl. Beryl structurally can have a lot of voids of crystallization and channels running through the gemstone, and those channels can trap other elements that are not part of the crystal structure and don't contribute to color. So for a colorless beryl, for something that you would expect to be fairly consistent in its density, it can have quite a range of densities depending upon what might have been trapped in those channels. Damburite is a rarer colorless gemstone, sometimes used instead of topaz because it's slightly more durable than topaz. It doesn't have the cleavage. It's got a small range, 2.97 to 3.03. Topaz, 3.49 to 3.47. Diamond, 3.5 to 3.53. Sapphire, 3.95 to 4.3. You get the idea. So they're the ranges of specific gravity. And these numbers, the ranges, represent the lower limits and the upper limits for the narrow region of test results, of which the majority of those species or examples of that species will fall between. And it is possible to get the occasional stone that tests outside those limits, and there could be reasons for that. Anyway, so general formula again, just to repeat, specific gravity is the weight of the stone in air divided by the loss of weight when it's weighed in water, which is equal to weight in air divided by weight in air minus weight in water. And then we sometimes write this formula with a ×1 at the end of the formula. And what that ×1 represents is that the liquid that is used to perform the hydrostatic weighing is water, because the density of water is 1.
Every single time I do that equation on my calculator, for some reason, if I don't put the end bracket in, it works. But if I do put the end bracket in, it doesn't work. But if you do the ×1 at the end, it works.
What calculator are you using? Is this just on the phone, or have you got a scientific calculator?
I've tried this on multiple calculators, because if you do gemstone in air divided by bracket, gemstone in air minus gemstone in water, close bracket, it doesn't work. But if you don't put the end bracket on, it works. However, if you do the end bracket ×1, it works. It's weird.
Hey, Louise, can I suggest try weight in air minus weight in water, do the reciprocal multiplied by weight in air in your home?
I'll try.
Good.
So if you were to use another liquid other than water that had a different density, then you would need to multiply your answer by the density of the liquid to make that correction back to what we print in standard gemological literature. Okay, so procedure for doing the specific gravity test. First of all, we check that the beaker is filled with purified or distilled water. Now, our teachers here, before every class, and it's usually David, he runs around and fills up and tops up the beakers with distilled water before you guys arrive. And water does evaporate during the day and over the course of a week, so we do need to top it up fairly frequently. The water level needs to be above the level of the basket, so the basket needs to be fully submerged in the water. So just take a minute when you're doing specific gravity in the lab and just have a look and make sure that that basket is beneath the surface of the water. I do have a funny story about this from a few years ago when we came in to do some cataloguing after the Christmas holidays, and the lab and the building had been closed up since exams in October. So all of the water in the beakers had evaporated, but stupid me didn't think about the effects of evaporation on the beaker, and we're trying to do specific gravity measurements in the lab, and it took us over an hour to realize that the reason why we were getting really stupid measurements was because there was no water in the beaker. So some of us do make really silly mistakes. And then when I make a silly mistake, I like to use it as, examples for you guys as to why we have procedures.
You mean exam questions?
Sorry? Adele?
Exam questions.
Yes, exam questions. I sometimes turn my silly mistakes into exam questions as well because it amuses me. It's like, yeah, but it's because I walked into that. So the beaker has to be filled. Check the wire basket is attached to the hanger above the beaker. That's also really important. We frequently, to remove the stone out of the water, you need to pull the basket out and tip the stone onto the bench beside you, and then you have to hang the basket back up again. Sometimes it's easy to not get the basket in its little hanger position and it kind of falls down into the beaker, but that won't give you the right answer for specific gravity. So make sure that the person who's used the instrument before you has hung the basket in the right place. Check the basket is completely immersed in the mortar. And then what we want to do is, while the doors of the machine are closed, we're going to tar the machine to make sure that it is recording that we're starting our measurements with a 0.000 balance. But sometimes these little instruments, they can wander a little bit and they can record a measurement when there's nothing there to be measured. And then that's going to affect our readings. The machine is really, really sensitive to airflow. So all of our measurements need to be done with the door closed. But to put the gemstone in the beaker, we need to open the door to get access to the beaker, but then we're going to close the door again. So we're always going to make sure the door is closed when we're obtaining the reading. We also need to make sure that we're standing clear of the table. And this sounds really, really stupid, and it is stupid. I'm not suggesting. I always hold my breath as well. That's just me, because I'm scared of the SG machine. So I even stand back with my hands in the air and hold my breath. But I don't suggest, that's not part of the procedure. You guys don't actually need to do that. If you lean on the bench, it may cause vibrations and affect your readings. The bench that we use, you might notice, is a really, really thick piece of heavy concrete. It's a really thick piece of heavy concrete so that any vibrations through the floor doesn't affect the machines, and the machines are really nice and grounded. But still, if you've got people leaning on the desk, it may affect the measurements. They're really, really sensitive little machines. First, we're going to weigh the stone in air, and the stone has to be clean and dry. Then we're going to record our results. Depending on the instrument, it may go to 3 decimal places or it might go to 4 decimal places. We're going to write down exactly what the instrument says to the full range of decimal places. Do not truncate your results, which means cut them off. Do not round your results because it'll lead to errors with your calculations. Then we're going to weigh the stone again by dropping the stone into the wire basket and then closing the door. This can be a little bit tricky because when we try to drop the stone into the basket, sometimes it misses the basket and it ends up inside the beaker, on the ground of the beaker rather than in the basket. And then it's a pain to try to fish around with your tweezers to grab the stone and pull it out. So you'll do that lots, miss the beaker. David and I have slightly different approaches to specific gravity. Do what works with you. I like to drop the stone from above the water and go doink into the basket. David likes to push his tweezers into the water and place the gemstone in the basket. He thinks he gets better results that way. I think I get better results by dropping the stone. Do whatever's good for you, but if you drop the stone from above the water, it sometimes misses the basket.
Laura, can I offer another suggestion? So given parallax, error and all the rest of it, I like to open the top slide and look straight down. So I'm looking down the stone, the tweezers, the basket, and then I can put the stone
Just
in.
line it up.
Yeah, line them up. It works for me.
So there is a glass viewing portal on top. You can open that up to give you better view. I'm a short ass. I can't see from the top. But if you're tall enough to see from the top, and no, Dell's a bit taller than me, but only a smidge. Not calling you a short ass, Adele. So you'll develop a routine that works for you. Be patient and wait for the scale to steady itself. It can take a couple of seconds while it kind of cycles through the numbers. Some of the scales may actually have a little round circle dot that will print at the end of the numbers when the scale is satisfied that it's stopped. Some of the scales may continue to wander a little bit, and it depends on the mood of the scale and the day as to whether it's going to wander or not, and that can be a little annoying. So if you stand there and look at the scale long enough, it will continue to increase the number. Specific gravity is not my favorite instrument. I have a love-hate relationship with this. We're going to write down our figures to 3 decimal places. I just said I have a love-hate relationship with this instrument. I never trust the measurements taken in liquid. I always do 3 measurements. So take the first measurement in liquid, take the stone out, close the doors, tar the instrument, dry your stone off, and then measure it in the liquid again. If you get the same result or only just 1 decimal place in the 4th position different, that's okay. If you get a result that is too far different, then do it a 3rd time. And sometimes I've gone to the extreme and I might have done it more like 10 times because it keeps being different every time because they're bastards. But if you do it twice and get more or less the same number, be confident in that number. If it's too different, do it a 3rd time. And I think it's acceptable to do an average of the 3 results that you get. But never rely on one result only in water, especially under exam conditions, because there's a whole lot of things with specific gravity that can go wrong. One of the pictures that I'll have coming up, you can get little gas bubbles or air bubbles attached to the stone, and that's going to affect the measurement. And it's often not possible to see that little bubble attached to the stone. But you don't want your one measurement to be tainted by a little air bubble that's been trapped. So do 2 measurements, please. Okay, carat weight. Carat weight, a lot of people who deal with gemstones on a daily basis will be aware of what a carat is. Carat is a unit of measurement for a gemstone, for how heavy that gemstone is. So instead of using grams or kilograms, we use carats. 1 carat is 1/5 of a gram, so 5 carats equals 1 gram. When we're doing specific gravity measurements, we can use either carats or grams. It does not matter, as long as both measurements in air and in water are done with the same unit of measurement. We can change the units of measurements on some of those scales, so it's just another thing to watch out for, that you don't want to hit the wrong button and change the units and record down 2 different units, because that'll already stuff up your calculations. Talking about 4 degrees Celsius, when we're measuring something like a corundum, at 4 degrees Celsius, it might measure 4.000. At 20 degrees Celsius, it might measure 3.99, which is still within the range for a corundum. And you've also got the errors estimates of like your machine, which we don't take into account as well. So this little slide here is just saying, don't stress about the 4 degrees. It's not going to impact our results for the purposes that we use them. Stone must be dry when it's weighed in air, and the stone must be clean. The stone can't also be a composite material. So something like a GTD, we're not going to do a specific gravity test on. We can do a specific gravity test on a GTD. There is nothing physically preventing us from doing the test. It's just that GTDs are a combination of two different materials with two different densities, and the ratios of the garnet to the paste is going to differ for each gemstone. So the specific gravity test, the result that we get is an amalgamation or an average between the garnet and the paste, and it's not going to give us any information that's going to help us identify that stone. So we don't waste the time in doing that test because it doesn't give us any good information. If you are in Gem 2 and end of year exams, if you do a specific gravity test on something like a GTD, you may find that you're penalised a small amount for doing a test that is inappropriate. But you can, of course, do a specific gravity test on a GTD. Other stones that we don't do tests on, things like beads, is also like a composite gemstone material because you've got something like a drill hole, and that drill hole can get air in it. And unless you are really, really good with teasing the air out of the drill hole while immersed in a liquid, don't try it. Something like a cultured pearl is also like a composite material because you've got the pearl, the nacre of the pearl on the outside, but you've got the bead that's on the inside also. Items that are set in jewellery is also like a composite material. And then you have some material that may be porous and absorb water when you place them in water. Australian opal doesn't tend to do it, but Ethiopian opal is what's known as hydrophane. And when you immerse it in liquid, it absorbs the water. And if you weigh it after you've had it immersed in liquid, it'll actually weigh heavier because you're weighing the water as well as the opal.
And it'll turn cloudy.
And it can go cloudy, depending on the opal though. Some of the opals will bring out the play of colour, it'll develop a play of colour where there was no play of colour, and some of them will lose a play of colour and go cloudy.
Yeah, I've got one at work at the moment that's giving me a headache because she brought it in and it had turned cloudy from like contact with all of her skin products. And I got the cloudy out from acetone only to find out it was dyed. So now I need to figure out how to re-dye it.
Oh dear. That's fun and fascinating.
It's very fun.
Yeah, so dyes that are used on gemstones can often be removed with acetone. I've got a friend who owns a bead shop and she buys in a lot of gemstone kind of beads from China. And before she puts anything out for sale, she tests how colour fast it is, if it's been dyed, if the dye will come out with acetone, because she needs to know to be able to advise her customers on whether the colour is going to be colour fast. I had heard about Ethiopian opal being dyed, but we haven't got any in the collection, so it's on my wish list. And maybe a bucket of it and a bucket of acetone so that all you guys can play. Okay, so we can get tiny little air bubbles attached to gemstones when they're immersed. Usually what we do is just perform the test again. Some textbooks suggest that using camel's hair, you can tease the gas bubble or the air bubble off from the gemstone.
You have a camel out back.
Sure. Yeah, or a dog. But yeah, I wouldn't bother trying to tease the air bubble off. I still don't trust the results that you get. Just redo the result. But last year, while I was testing some of the garnets, I got a really nice little gas bubble that was really obvious and came up really nice in the pictures. So this is what a little gas bubble or air bubble may look like when you get it trapped in the gemstone. And sometimes as the gemstone falls into the liquid, it just brings down some of the air and it gets trapped. So this is a fail and we need to repeat the process again. Some gemstones are too small and too light to break the surface tension of the liquid, so they will float on the surface of the liquid. Diamonds, because they're made of carbon-based material, they're hydrophobic, so they are repelled by water they can't be wet by water. So for a diamond of about 25 points and under, because of its hydrophobia, it will sit on top of the water. It won't go underneath the liquid. It won't be wet by the water. So that's another thing just to look out for. This little green gemstone here, this was a tourmaline. It's not a diamond. And we were trying to work out if we wanted to keep it in the collection or whether we wanted to pitch it. And we're trying to find out if there was any redeemable reason for keeping it. It was about 3.5 mil round. It was really difficult to take a refractive index from, and it floated in the beaker. So we decided to piff it from the collection. But I got a really good photo of it floating before we did that. So yeah, we try to keep stones in the collection that are not going to give you guys too much problem. But second year, I know the teachers like to at least give you one stone during the year that's going to surprise you by floating on the water. And I know Adele has fun stories from when she was given a stone that floated.
Well, the jolly thing bounced. It didn't just float, it bounced. I repeated the test 3 times. Finally, I did the David method. I picked it up, I shoved it in the basket, I held it down, and guess what? 3.52. It was a diamond.
Diamond. Yes. So to overcome the effects of surface tension in water and for drag of the basket, a tiny little bit of detergent in the water can help. The water that we use is all distilled, and David puts in a little bit of detergent so that stones try to behave themselves. Additional information. Density is not just important for identifying a gemstone, but because of density, it can also affect the size of the gemstone relative to the weight, which is really, really important if you're a jeweler ordering gemstones. A lot of jewelers will work primarily in diamonds, and round diamonds of calibrated shapes. The calibrated sizes are very predictable in their weights. But when you move to other gemstone species that have other densities, the same millimeter weight will give, same carat weight will give a different millimeter size. So if you're in a position of ordering gemstones from a colored gemstone merchant, it is better to order in the millimeter size that you want, not the carat weight that you want, because each gemstone is going to be different. So for an example, a 3 mil round diamond weighs 10 points, 5 mil round diamond weighs 47 points, 7 mil diamond weighs about a carat 28. And round diamonds with a standard round brilliant are fairly consistent in their measurements because the stones are not cut too deep or too shallow. But I went through a couple of years ago, I pulled out every 7 millimeter size stone I could at work. And coloured gemstones are not always cut in calibrated sizes either. So I didn't have 7 mil round stones, but I pulled out 7.7 or 7.6 or 7.2. And depending on a range of factors, of which density is one factor, the carat weights of these stones varied enormously. Emerald is very, very light. So you get a much larger size and still a small carat weight. So 7.4 mil round emerald was a carat 40. The diamond, 7.5 mil round diamond, which I borrowed from the merchant next door, was a carat 58. The spinel, 2 carat 67. So there's a good range of carat weights for a similar diameter. So you've got the density, but you've also got the cut style. So is it cut over deep? Is it windowed? Is it bellied? A lot of coloured gemstones, instead of being cut in a V, they're kind of cut in a U shape and they're bellied. So there's a whole lot of factors that can contribute to that. Valuers who are valuing jewellery, and if the stone is set in jewellery and they can't take the stone out to weigh it, they have calculations or formulas that can estimate the weight of the gemstone. And for round gemstones, the carat weight is given by the diameter squared times the depth of the gemstones times the specific gravity of the gemstone times this factor 0.0018, which is the modifying factor for the volume of the standard round brilliant. But then you also need to modify it slightly. If it's got a thick girdle, you add on 1 or 2%. If it's bellied, you might add on 5 or 10%. If it's shallow, you might take off 5%. And then if you get anywhere within 10% of the actual weight, you're doing good. So girdle thickness, shape of pavilion, blah, 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 blah. Anyway, the GAA notes give another way of estimating the weight based on the specific gravity. So for a diamond of about 6.5 mil round that weighs about a carat, for quartz or emerald over 6.5 mil round, it's going to be about 25% less in weight than the diamond. The tourmaline or sapphire of 6.5 mil round will be a 15% more than the diamond, and a zircon of similar size will be about 30% more than the diamond. So a carat 30 rather than a carat. Anyway, into fluorescence. Now this was the picture that I was talking about with Adele earlier, because I was noticed here long wave on the left, short wave on the right. And I'm going to have to go back to my stones at home because this is opposite to what we usually print in literature. Scapolite will have a typical fluorescent response of an apricot or a pinky orange color under long wave light, and under short wave will be weaker or inert. But I've checked my records on my phone and I've got 6 stones that I've recorded down as being almost inert under long wave and very strong under short wave. So I will check that for you. It could be that one particular deposit of scapolite had a fluorescent response that was inconsistent with other deposits, which sometimes happens if the chemistry of the trace elements of one particular mine is different to what had previously been recorded. So this is an example of the fluorescence, and I've picked scapolite in particular because it's a stone that is fairly reliable in its fluorescence response. You will see a colour, depending on which light source you use. And scapolite is also a stone that can be a little bit of an imposter stone. It has overlapping refractive indices with quartz. It can appear to be a similar colour to quartz. It has similar specific gravity ranges to quartz. Scapolite is part of a solid solution series, and depending upon which end member is more dominant, you may have a specific gravity that overlaps, or it may be significantly different to quartz to be able to separate it. But generally, scapolite is seen as a stone that gives a lot of trouble to students to identify. Quartz is always uniaxially positive. Scapolite is always uniaxially negative. Quartz is always inert to ultraviolet light. It doesn't fluoresce, whereas scapolite tends to show a very distinct orangey apricot type colour to ultraviolet light. So if your pale yellow stone fluoresces, it's unlikely to be a citrine, and think about it being scapolite. So before we start talking about fluorescence, we're going to do a little bit of revision on atomic structure again with the atom. We're just going to remind ourselves that an atom is comprised of subatomic particles. We have a nucleus, which is heavier, which comprises about 99% of the weight of the atom. And the nucleus contains neutrons, which have no electrical charge, and protons, which each have a single positive charge. And then surrounding the nucleus is a cloud of negative energy, and that negative energy is comprised of another subatomic particle known as a electron, and each electron has a single negative charge. And then that cloud of negative energy arranges itself into layers, with the innermost layer or shell containing a maximum of 2 electrons, and then the next layer out containing a maximum of 8 electrons. With those shells, those electrons tend to group up into pairs of 2. And we've already discussed when we were doing the pleocroism and the selective absorption of light, we discussed the transition elements that all had an unpaired electron in the valence shell. So just remembering that unpaired electron and that valence shell, we're going to be revisiting that because it's those same elements with the unpaired electrons that also cause fluorescence to be seen in gemstones as well. So I'm going to skip over this. So some minerals, when they're placed under ultraviolet light, will fluoresce. And what that means is that they're taking a higher energy form of light or a higher energy form of energy and transforming it into visible light. When we transform it into visible light, energy can't be destroyed. So the remaining energy is transformed into heat energy or vibrational energy. So we're taking a form of energy, ultraviolet light, which our eyes can't see, and the gemstone is transforming that into a lower energy source of visible light, which our eyes can see. And there's only about 15% of minerals which will fluoresce when placed under ultraviolet light. So most minerals are going to be inert under ultraviolet light, and it's only those minerals that have those unpaired electrons in the valence shell which are going to respond to the ultraviolet light and cause that transformation and cause that visible light to be emitted by the gemstone. So fluorescence is where the emitted light occurs at a longer wavelength than the light that's incident upon the surface. So remembering that the visible spectrum extends from 400 nanometers in the deep violet to 700 nanometers in the red. The visible light is the longer wavelength. So the ultraviolet light is all less than 400 nanometers, but it's also a higher energy form of electromagnetic radiation. So the ultraviolet light has higher energy, but shorter wavelengths. There are 2 different types of wavelengths that we use for ultraviolet light in gemology. We've got the short wave and we've got the long wave. And that's because the short wave has the shorter wavelength and the long wave has the longer wavelength. So we do 365 nanometers and 254 nanometers are the 2 wavelengths of light that we use. So what's happening when the object fluoresces? The ultraviolet light, when it comes in contact with the gemstone material and interacts with the unpaired electron, that unpaired electron, just like when it interacts with visible light, it reacts with the ultraviolet light and it takes away parcels of energy. And the parcel of energy that it takes on board makes that electron more excited and gives it more energy temporarily, and that electron jumps up to the next energy level or the next shell. But it can't sustain that level for long, and it drops back almost instantaneously back to its ground state. And when it drops back to the ground state, it releases the energy that it had taken out of the ultraviolet light. And when it releases that energy back, that energy is split between visible light, heat energy, or vibrational energy. And it's that visible light portion that we see as fluorescence that's being emitted by the gemstone. So light energy is taken in by electrons, and that electron then jumps up to that higher energy state. So the amount of energy released depends on the particular atom, and it depends on the size of the valence shell and how far that electron is jumping. The amount of energy is often measured in electron volts, and we don't need to go into the detail of how we calculate the electron volts. We can go into detail of things called electron band gap theory, but we're not going to do that either. But depending upon which atom it is, the electron will take a very specific size parcel of energy, and then it gives back that same parcel of energy but transformed into light and heat. So we see commonalities between these transition elements. Not all transition elements will fluoresce, by the way, but some of them, if they're an activator, will produce the same color fluorescence in different types of minerals. So coming back to chromium, chromium can cause a red color in ruby, or it can cause the green color of emerald. And when it fluoresces, it always produces a red color fluorescence. So fluorescence is a very rapid process. It requires less than 10 to the -8 of a second to occur, which is 0.0000001 of a second. So that's how long it takes for the electron to take the energy and give the energy back. And fluorescence is a continual cycle. As long as that ultraviolet light source is there, those little electrons are bouncing up and down and emitting that visible light. And then standard fluorescence, when the UV light source is turned off, that process stops. With some gemstones, Cooper PD opal is one example. When the light source is turned off, there is a very slow release of visible light for a couple of seconds afterwards. And that's a different type of fluorescence.
Is it just an opal that's found? Are there any other common stones?
Acmanite.
Acmanite. Acmanite, I've got some treated amber at home that also phosphoresces. Synthetic. You've got phosphorescent amber? Yeah, I've got some green amber that was treated. Synthetic diamonds, HTHP synthetic diamonds will phosphoresce. Yeah. That's one of the screening tests that we have to distinguish natural and synthetic.
Do
and
they
the method.
Do they fluoresce yellow?
They can, but natural diamonds can also fluoresce yellow. So it's very complex, the range of colours that they can fluoresce. And the amount of phosphorescence. It's very rare to get phosphorescence in a natural diamond.
So maybe opals, synthetic diamonds.
Yeah.
And some ambers.
And some other rare minerals. Okay, so I've covered that. So where fluorescence is the absorption of energy from ultraviolet light and the re-emission of a lower energy, phosphorescence, which is what we're talking about with the opal, is the slow emission of light from the excited state back down to the ground state, and can take 1 second or longer. 1 second is a blink and you'll miss it. You're not really sure if it's really there. If it's 6 to 8 seconds, you've got a chance of seeing it. You will see it. Some of the HTHP diamonds, when viewed in the right environment, will phosphoresce for 4 or 5 minutes or longer. But opal tends to be, depending on if it's natural or synthetic, somewhere between 1 and 6 seconds. Both fluorescence and phosphorescence is a type of luminescence. So we have activators and we have quenchers. For fluorescence to occur, it has to have an activator present. So an activator is an element that has an unpaired electron, and that element contributes to fluorescence. Some elements with unpaired electrons, such as iron, act as a quencher, and instead of emitting visible light, they transform all of the energy into heat and vibrational energy, and they actually stop fluorescence from happening. So there's only a small list of activators, and some of these may even be quenchers in different gemstones. So for the majority of times, these are considered activators, but they may also be a quencher under certain circumstances. So we've got manganese, chromium, titanium, copper, lead, europium, cerium, uranyl, tungstate, molybdate, sulfur, and nitrogen.
What do you mean by a quencher?
So an activator is an element that causes fluorescence to happen. A quencher is an element that will stop fluorescence from happening. Manganese is responsible for the red or orange fluorescence in calcite, which is frequently seen, green in willimanite, which is a collector's mineral and not a gemstone, or the yellow in esperite. I've had to look for minerals that are not used as gemstones because it's so infrequent to have an actual gemstone coloured by manganese that fluoresces. For example, manganese colours the spessartine garnet, it colours it orange, but spessartine will always be inert because it forms a solid solution with almandine, which has iron in it, and the iron's going to act as a quencher and stop any fluorescence. Uranium may produce a yellow-green reaction in some minerals, and it's believed that the mustard yellow reaction that we expect to see in zircon is due to the uranium that's present. And chromium is responsible for red reactions in ruby and emerald. So it's only going to be about 15% of minerals that fluoresce, and it's usually consistent which elements are responsible for those fluorescence and what colours we're going to see from the fluorescence. The mustard reaction in zircon can also be due to rare earth elements present in zircons. And the activator works because of the unpaired electron in the outer orbit of the atom. Quenchers work by absorbing the energy and transferring it to heat and vibrational energy, and iron is the best known quencher within the gemstone kingdom. So many gemstones contain iron as an essential component of their structure or as a trace element contributing to colour. So any mineral that contains a large amount of iron is not going to fluoresce. So that's why so few gemstones fluoresce, because most of them have iron in them. So the light waves that we use, long wave UV 365, short wave UV 254. The short wave has the smaller wavelength compared to the long wave light source. And there's an easy way to remember it. Long wave UV, there's 365 days in the year, and just remove 1, 1, 1, and you get to the short wave UV. A little bit of how many? No, I think I'll leave it there because that's too much. We'll pick that up, I think, after mid-year exams. That sounds scary. Question?
The tutorial on Thursday.
Yes.
Who is taking the tutorial?
Me, Adele, Dorothy. That depends on whether Adele's doctor says she can come.
And David said.
And David's online.
He said we'd be able to get the answer documents.
David likes to give out the answer documents, and Adele and I don't like to give out the answer documents.
Can we have David's?
Yeah, David's
Just after we've done it.
When we're finished.
After,
Yeah.
for study purposes.
So start for the exam for all three.
I think I'm going to have to say yes, because David will give it out to his group,
That
and
would
then
be
that's
an
kind of
up-level playing field.
yeah. And I've tried asking David not to give out the answers, and he just says no.
Yeah.
So
Maybe he
Yeah.
can give us the other two.
No, David ganged up on us with Laura and me, and he said, well, how many years experience have you got? How many years experience have I got? I trumped the two of you together, so I'll do what I want to do. And we
Yeah.
lost.
We love David for that.
I know you do.
Or have it on daytime or nighttime?
sorry,
Is the exam on
nighttime.
nighttime?
Thank you for asking.
Nighttime. So yeah,
So Laura, do I need to send you an email to ask for a request for the?
Please.
I've
because
got.
I'm very bad at remembering
That's
stuff,
okay,
especially at the end of class.
I would actually, I have a preference to come in, but I have an interview in Hillsville at 3:00. So I'm just not going